Welcome back, everybody. We're going to start off where we left off, which was with 3.4, where we're going to actually now, instead of being given random information about a graph and then figuring it out. Oh, we forgot to erase our little lines on this problem. Those are just supposed to help us draw things, but now we'll go ahead and go on to an actual problem where we are going to find everything. So the function, we're going to sketch the graph of f of x equals 3x to the fourth, 3x squared, excuse me, divided by x squared minus 1. Did I really change it up? Yeah, that's... Oh, we already did this one. That's right. So we're going to do a quadratic or a rational function. Sorry, I promise I'm working on things. So first and foremost, we're going to be finding domain. This is 3x squared over x plus 1 times x minus 1. So the domain, which I'm going to just jot off on the side here, is going to be negative infinity to negative 1 union negative 1 to 1 union 1 to positive infinity. Because it's the only places where this function doesn't exist is where its denominator equals 0, which would be at 1, negative 1. So those are the only places that are problematic. Next thing, we're going to find our intercepts. Any easy information that we already know from pre-calculus and stuff. So intercepts, that would be setting the function equal to, for the x-intercept, that's setting the function equal to 0, setting your y values equal to 0 and solving. So that's going to be 3x squared over x squared minus 1 equal to 0, which gives us 3x squared equals 0, which gives us x equals 0. For the y-intercept, it's going to be the same thing, but just so we have it in our notes on how we find a y-intercept, that's setting x equal to 0, which is the same thing as finding f of 0. F of 0 is equal to 0 over 0 minus 1, which is 0. So we just get the point 0, 0. That's all we get from there. Another thing that we want to find are asymptotes, if the function has any. The polynomial before, polynomials don't have asymptotes, but rational functions do. They have vertical asymptotes wherever the denominator equals 0. So VAs at x, VAs where denominator equals 0. So x plus 1 times x minus 1 equals 0, which gives me vertical asymptotes at x equals negative 1 and positive 1. And then we also have to find HAs. Horizontal asymptotes. When it comes to a rational function, what do? I mean, technically speaking, like if you remember from 126, you look at the ratio, like you look at the degrees to figure it out. But we can also do it with calculus. We can do it with calculus by doing the limit as x approaches positive infinity of 3x squared over x squared minus 1. And do you remember how we do that? If we're doing a limit at infinity, we look at the highest degree terms. So this would be equal to the limit as x approaches positive infinity of 3x squared over x squared. The x squareds cancel, and it equals 3. So we have an HA at y equals 3. Any questions so far? Technically speaking, I should also check the limit as x approaches negative infinity. But because this is a rational function, it's only going to ever have one horizontal asymptote. But you can definitely check it and verify it for yourself that the limit as x approaches negative infinity would be the exact same thing, right? Nothing's going to change there. The only situations where we get two horizontal asymptotes are if I tell you, like in that previous problem, this one up here, right? I told you that the limit as x approaches negative infinity was 4 and it approaches positive infinity is negative 2. That's why we got two of them. The only other way we would get it with an actual example such as this would be if you had square roots. That's when we got multiple horizontal asymptotes. But either way, we get HA at y equals 3. That's all the preliminary info. Now let's work on finding intervals of increase and decrease along with relative extrema. And then after that, we'll work, and that corresponds to the first derivative. Then we'll work on concavity and inflection points, which will correspond to the second derivative. So now we're going to do increasing, decreasing. So f prime would be f prime g. So 6x times x squared minus 1 minus g prime. So 2x times 3x squared. Wait a minute. What am I doing? No, that's fine. That's all fine. Cool. Divided by g squared. So x squared minus 1 squared. And we're running out of space already. So what I'm going to go ahead and do is I'm going to do the little tiny bits of simplification. And that is going to equal negative 6x over x squared minus 1 squared. So if we're going to set f prime equal to 0 slash DNE, that's going to give me x equals 0, 1, and negative 1. 0 from the numerator, 1 and negative 1 from the denominator. But remember, those are two places where the function doesn't exist, right? F of 1 and f of negative 1 do not exist. So 0 could be a critical value. It could be a relative max or min, but 1 and negative 1 cannot be because you can't plug them in. But either way, we've got those values. We'll make a sign chart. Negative 1, 0, and 1. And this is f prime. I'll do the test values. X equals negative 2, x equals negative 0.5, or you could do negative 0.99. Doesn't matter what you want to do, but negative 0.5 seems to be good enough. X equals 0.5, and x equals 2. And remember, this negative 6 plays a role. It changes sign. Positive 6 wouldn't do anything because positive numbers don't change signs, right? A positive number, if you multiply a negative number by a positive number, it stays negative. If you multiply a positive number by a positive number, it stays positive. It's only with the negative numbers that we have an issue. So I'm going to make sure that's mentioned. So that's always going to be that negative there. And then the 6x, the x will change. So if I plug in negative 2, it's going to be a negative. And then the denominator is always positive because it's squared. Always positive because it's squared. Plug in negative 0.5. So that's a net positive, right? Because it's negative times a negative over a positive. That's going to be a net positive. So it's going to be increasing here. And then I'll plug in negative 0.5. The x will also be negative, and the denominator is always positive. So once again, it's a net positive. Plugging in a positive 0.5, the x would be positive. And as per usual, the denominator is positive because it's being squared. So that's a net negative. And then if I plug in positive 2, it'll be plus divided by a positive. And that'll be a net negative. Any questions so far? If there are. So good news is that we don't even need to worry about negative 1 or 1 being critical values because they're not. It goes from increasing to increasing, so it wouldn't be like a relative max or relative min. But if we did see that, we'd have to remember that if we, and the good news is, honestly, if you try and plug in f of negative, like you're going to be graphing this, so you need to know what the values are. You need to know the y values. But if you try and plug in negative 1, you'll see that f of negative 1 doesn't exist. Same thing with f of positive 1. So that's a good thing when it comes to graphing that you don't have to worry about it. But you have a relative max, increasing, negative infinity to negative 1, and from negative 1 to 0, decreasing from 0 to 1, and then from 1 to positive infinity. Relative max at x equals 0. And since we need to find the location, f of 0 is equal to 0, just as we already calculated up above, right? F of 0 was equal to 0, so it's going to be the point 0, comma 0. And there's no relative min. Any questions so far? Yes, right.
So we plug in the semi-critical values to define it as increasing or decreasing. Now we plug it in, but like
Yes, we put it in the sign chart because it can affect things. It doesn't necessarily do it in this problem, but it can. So semi-critical values still play a role. Yes. All right. Then we got to do concavity, unless there's any other questions. Concavity and inflection points, that's going to require the second derivative. So I'll use the simplified version. And I deliberately did this problem because there's a lot of algebra that we need to learn about, learn little tricks and tips, right? When you're learning how, like if you're trying to fix up your house or anything like that, if you're trying to take care of a hole in the wall, you learn little tricks along the way that make things easier. Like I'm terrible at it, but I know that like if you make a hole in the wall for whatever reason, you're supposed to cut out kind of a nice square, right? And then so that you can put a nice piece of drywall into that spot with a people like do like a little 2x4 right on the back. Somebody know what I'm talking about? So like you learn little tricks as you go along, and this is one of those tricks in mathematics. So f double prime of x be f prime g, so -6 times g, which is x squared minus 1 squared, minus g prime, which I'm going to put in brackets, which will be 2 times x squared minus 1 to the first power times 2x, times f, which is -6x, all divided by x squared minus 1 squared squared. So we're going to have to shove this in here. Like we're going to have to do a lot of algebra. But one option would be to FOIL it out and do it all by hand. Sure, we can do that. You know, square the x squared minus 1 here, distribute the -6, FOIL this together and FOIL it in and do that. But I wouldn't recommend that. That's going to be a very, very tedious adventure. Do you guys see anything in common that you can factor out? There's a common factor of x squared minus 1. In the two terms in the numerator, there's a common factor of x squared minus 1. So I'm going to underline, or I'm going to highlight it. They have a common factor. So we might as well take that out. So this will equal x squared minus 1 bracket -6 times x squared minus 1 minus 2 times 2x times -6x, all divided by x squared minus 1 to the 4th, because it'll be 2 times 2, because a power raised to a power, you multiply the powers. And aha, one of those will cancel. Yay. And since we're not completely wiping out the factor, we're not getting rid of all this, like we're not getting rid of any problem, like any important data values. So cross that out. And then this will be, okay, so you get -6x squared plus 6 plus 24x squared. So that ends up being, at the end of the day, 18x squared plus 6 divided by x squared minus 1 cubed. It's a lot of algebra, so please take a second to make sure you're with me. So if you have any questions, feel free to ask. But that's a little nifty trick that you can do. If you're really going to have to simplify something, see if there's any common factors to make it easier on yourself. It wouldn't be wrong to FOIL it out. It's just, it's going to take a lot of extra work. You know what I mean? However, in some situations, if you don't factor it out, it'll make it really, really, really difficult for you to factor. You'll have to bust out the rational zeros theorem, or beg me for the zeros of it. Tell me how, like Bill, please tell me the factors. I'd be like, okay, sure. But anyways, x squared plus 6 over x squared minus 1 to the third power. So we're going to set the second derivative equal to 0 slash where it does not exist. That'll give me 18x squared plus 6 over x squared minus 1 cubed equaling 0, and where it doesn't exist. And the only values that works for are x equals 1 and -1. But John Doe student writes this, so don't write this in red. But John Doe student says plus or minus the square root of 1/3. He's not right. The numerator is a sum of squares. It's 18x squared plus 6. So it can never equal 0. I'm going to write that down, actually. That's why John Doe student is wrong. So never equals 0. So no, just never equals 0. So we don't have to worry about that. So we only get -1 and 1. And I think we can fit this down here. You guys think we can? It's a pretty small one. So only 2 critical, like not critical values, but you get what I mean. X equals -2, x equals 0, and x equals 2. Of course, you can use multiplicity tricks, but this is a little bit more challenging since I didn't factor the x squared minus 1. But -2, the numerator, you don't even need to plug it in. It's always positive because it's a sum of squares. But you can still do it if you want to. You get a positive, plug in -2. -2 squared is +4, minus 1 is +3, cubed is positive. So it's concave up here, because if you're positive, you're feeling positive, you got that smile. Plugging in 0, the numerator, once again, is still positive, but then you're going to get 0 squared minus 1. That will be -1 that you're raising to the third power. And if you raise a negative number to an odd power, it stays negative. So it's going to be negative here, which results in a net negative. And if you're negative, you're feeling down, and you got that frown. So you're concave down. And last but not least, plug in 2. You'll get the same thing. The numerator is positive. Denominator will also be positive, so it's a net positive, which means it's concave up. Are 1 and -1 inflection points then? Yes, I see some yeses, I see some nos. The answer is no, they're not inflection points. But why? Let's look back at the original function. The domain of this function is all values except for 1 and -1. You cannot plug in 1 or -1 into the function, so they're not inflection points. In order for it to be an inflection point, you need the concavity change, and the function needs to exist there. So we can even write that as a little note here. X equals 1 and -1 are not inf points because f of plus or minus 1 does not exist. But we do now know the concave up and concave down situation. We know it's concave up from -infinity to -1, and from 1 to +infinity, it's concave down in between -1 and 1. So, and I forgot to label this f double prime. Now what I do, I've got everything I need. I'm going to draw my little cheat sheet. And so my first derivative had -1, 0, and 1. And sure, we'll just go ahead and do it based on that. So this is 0, 1, and -1. And then the second derivative had -1 and 1. And then we split it up based on any tick mark that we had, regardless of whether it was the first derivative or second derivative. Because they both affect the curve. So if you're increasing, but you change concavity, the curve is going to change its structure. It's going to change in shape. That's why you need to draw a line in every single tick mark that you have. So let's fill in our graph. It was positive, positive, negative, negative. So increasing, increasing, decreasing, decreasing. And then for this one, it was concave up, concave down, concave up. And I draw the overall like concavity or increasing lines and curves on the whole thing so that I don't get confused and forget to do it somewhere. So that's what I typically recommend. Instead of just so what I'm saying is don't write this, because that can be a little bit small and it makes you forget that that's concave up on the whole thing. So my recommendation is to draw a big smile here. Because we're doing math, we're gonna have a great smile. We're gonna have we love doing this stuff. Okay, so increasing means you're going up, but you're concave up, so you're curving upwards. So that would be like this. Fill in the rest of the chart. If you could, please. I'll slowly fill them in. I got that. And so you can either use that little cheat sheet thing that I shot, but I'm realizing now that this, if we remember that concave up means you're curving upwards and concave down means you're curving downwards, then we can just take the increasing, decreasing situation and then bend it the way we need to. So as I said before, you're increasing, so you've got to be going up, but you're curving upwards. That would mean this type of a shape. Here, you're increasing, but you're curving downwards. So that'd be going up, but curving down. So that's why it's this shape. Then you're decreasing, so you're going down and you're curving down, which is why it's this shape. Then you're decreasing, but you're curving upwards, which would be this shape. So we can either divide, then what I recommend is just drawing lines. Actually, I'm going to do a solid white line, a solid gray line through -1, though you can't even really see that, through 0, and through 1. That'll just help me with everything. Now I'm going to plot points that I know and any information that I had from earlier on. So I had an x-intercept at 0, 0, a y-intercept at 0, 0, but that's already plotted. I had a vertical asymptote at -1. And +1. And then I had a horizontal asymptote at y = 3. I'll draw that. 1, 2, 3. It's right there. Then I found a relative maximum at 0, 0, but I've already plotted that. And I didn't have any inflection points. So now I've plotted in all my preliminary information. Now I just need to fill in the graph. So I have to make this shape. So it can't be this because it has to hug its asymptote, right? It has to hug its asymptote. And it has a horizontal asymptote at 3. So what I have to start off with is this shape. By similar reasoning, in between -1 and 1, it's going to make kind of an upside down U shape. Because 0, 0 has to be a relative maximum, so it has to be at the top of a mountain. the top of a hill, and it needs to hug its asymptotes, so that's what it's going to look like. And last but not least, it should be shaped like this, so it has to be this portion. There's no other way for it to hug the asymptotes and also have that curve that we've drawn in our little cheat sheet. And I'm pretty happy with that, but remember, you can make it as interesting as you'd like. If you want to really make this dramatic, you can do that. Your prerogative. Not a big deal of either way. Any questions on that? Okay. Everyone's favorite. Trig functions. Yeah. Let's do it on 0 to 2 pi, because otherwise this thing is period. This will be periodic, so that will make things annoying. So we're just going to restrict ourselves to 0 to 2 pi. So the domain is everything. Domain is, well, actually, it's 0 to 2 pi. We've restricted it, and sine is defined everywhere. So of course it's defined on 0 to 2 pi. X is defined everywhere. So it's of course defined on 0 to 2 pi. X-intercepts. Trying to set x minus 2 sine of x equal to 0. That's a tall order to find out where it equals 0. There's only one spot actually that it does. Wait, no. There might be two. Yeah, there are two, but finding them is a very, very daunting task. It requires using a thing that we actually are not going to study in this class, but it is a calculus thing, Newton's law of approximations. So you have to do that to figure out roughly where it is. But even then, it's very, very challenging. So no easy x-intercepts. And then y-intercepts. G of 0 would be 0 minus 2 sine of 0. And sine of 0 is 0. Right? You use the hand trick, or you can use your calculator, but sine of 0 is 0. So we have a y-intercept at 0, 0. That's also an x-intercept. So I guess technically speaking, we had one easy x-intercept, but I wouldn't have been able to really find it from doing setting the function equal to 0. Vertical asymptotes, there are none, because this isn't like tangent. Tangent has vertical asymptotes. Secant and cosecant do, but sine doesn't and x doesn't. So no vertical asymptotes, no horizontal asymptotes either. So we can move on to the increasing, decreasing, and so on and so forth. So increasing, decreasing. We got to find the first derivative. So g prime of x will equal 1 minus 2 cosine of x. The derivative of sine is cosine. And then setting g prime equal to 0 slash dne is really telling me to set 1 minus 2 cosine of x equal to 0. And that's going to say cosine of x has to equal positive 1/2, because it's going to be negative 1 divided by negative 2, which makes it positive 1/2. And okay, got to remember our trig equations. When does cosine equal 1/2? Between 0 and 2 pi, that is. So once again, I think I've mentioned this before. I don't have my unit circle memorized, never bothered. I just remember the 3 different triangles. There's the big one, the 60 degree. There's the medium one, the 45 degree, and the small one, the 30 degree. And cosine corresponds to the x. So I want it to be the smaller one. Like I want my x value to be the smaller one. That's the 60 degree angle, right? That's the pi over 3. But cosine is positive in the first and fourth quadrant. So I also have to do this one, where this angle is pi over 3. But that's not, that would be negative pi over 3. I want the angle between 0 and 2 pi. You guys remember what that one is? 5 pi over 3. You can do it in a myriad of ways. One way would be to count it up. pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. Or you could do 2 pi minus pi over 3 to get the 5 pi over 3. But those are the two values. Pi over 3 and 2 pi over 3. X equals pi over 3 and 5 pi over 3. Those are critical values because those are spaces where the derivative equals 0 and g of x is defined everywhere. So it's going to be defined at those values. Those are critical values. We'll set up our sign chart. But instead of drawing arrows on the ends, I'm going to draw brackets because this is only defined from 0 to 2 pi. And then I'll plot pi over 3 and 5 pi over 3. So this is where things become a little bit more challenging on like for some of us. I need to plug in some test values. So I'll plug in what's so you could do like 0.1 if you really wanted to. Pi over 3 is approximately 1 point something. So you could do x equals 0.5 or x equals 0.1 and plug that in. Or if you want to be a total trig BA, right? A badass, right? If you want to be that person, you'd pick like pi over 6 or pi over 4, which is what I'm going to do. Pi over 6. Then I need to pick a value between pi over 3 and 5 pi over 3. That's between 1 and about 3. 1 and about 3. So you could pick 2, or no, a little bit more than 3. So like 1 and, between 1 and 2-ish. Right? Between 1 and 2. How much is 5 pi over 3? I don't know that off the top of my head. Embarrassing. Not really. 5. It's 5. Sorry. About 5. So you could pick 2, 3, 4, something like that. But I would recommend a very, very useful number between pi over 3 and 5 pi over 3 would be pi. And then 5 pi over 3 and 2 pi. There's only one I can think of, which would be 11 pi. Yeah, 11 pi over 6. Once again, though, you can use test values. Just make sure your calculator is in radians, which it should be. We haven't needed to switch at all. But you could definitely just as easily choose like x equals 6 for the third section, x equals 3, and x equals 0.5. You could totally do that, and everything will still work out just as well. But this way, I don't have to use my calculator. That's the reason why I wanted to do it. I know that pi over 6, cosine of pi over 6 is square root 3 over 2. So this will be 1 minus square root 3. That'll be negative. And so it's going to be decreasing here. Cosine of pi is -1. So it's 1 minus 2 times -1. So that would be 1 plus 2. So it's positive here. So it's going to be increasing. And then at 11 pi over 6, that would be, you're in the fourth quadrant. So cosine is positive square root 3 over 2. So 1 minus square root 3 over 2, 1 minus 2 times square root 3 over 2, that's negative. But you can always use your calculator. Totally chill. Totes chill to do. So it's increasing from 0 to pi over 3 and 5 pi over 3 to 2 pi. Decreasing from pi over 3 to 5 pi over 3. Wait, flip that around. Flip that around. Sorry. Decreasing between from 0 to pi over 3 and 5 pi over 3 to 2 pi. Increasing from pi over 3 to 5 pi over 3. And then there's going to be a relative max at x equals 5/3 or 5 pi over 3. And g of 5 pi over 3 would be 5 pi over 3 minus 2 sine of 5 pi over 3, which will be, I'm going to need my calculator because that's not going to be a nice number, right? 5 pi over 3 is not a nice number, so it'll be very, very hard to figure out how to plot that. So 5 pi over 3 minus 2 sine of 5 pi over 3 gives me 6.96-ish. Sorry, like approximately 6.97. So I have a relative max at 5 pi over 3 comma 6.97. And we have a relative min at x equals pi over 3. And to find the point, I'd plug it into the original function. So g over pi over 3 is going to be approximately, if I plug it in the same way, I should get negative 0.68, approximately. So we have the point pi over 3 comma negative 0.68. Whew, okay, that was a lot. But let's talk through it. So remember, the first derivative test is that sign chart, and it tells you where it's increasing and decreasing, and any place that you go from decreasing to increasing is a relative minimum. Any place where you go from increasing to decreasing is a relative maximum. It's gonna go up and then down. So you gotta reach an apex at some point. And then what I did is I wrote down the intervals. I don't necessarily need to on this problem because I'm going to be just using that to graph it. So I don't need to, but it's good to have it written down. And then the relative max was at x equals 5 pi over 3, but I need to find the actual point since I'm going to be graphing it. So I plug it into the original function to find the y coordinate. That's increasing, decreasing, and relative extrema. Now I need to go to concavity. For concavity, I need to find the second derivative, g double prime of x, which will equal derivative of 1 is 0, derivative of negative 2 cosine x would be positive sine of x, positive 2 sine of x. So g double prime equaling 0 is going to give me 2 sine of x equaling 0. So when does sine of x equal 0? 0, pi, 2 pi, every multiple of pi. Negative pi, negative 2 pi, negative 3 pi, negative 4 pi. But that's going to be x equals 0, pi, and 2 pi when we're dealing with the interval from 0 to 2 pi. So now that we've got that, we'll make our sign chart. And we're just going to make brackets on the end once again, because those are the endpoints. We're only working on that small interval. By the way, make sure, so there's no graph listed because we're going to have to hand draw this graph. So just leave at least a little bit of space down here, okay? But the only critical value, like not critical value, but essentially a critical value is right here at x equals pi. So we'll test a couple test points. What's a good angle? I mean, so that's any number between 0 and 3.14 will work for this interval if you really want to. But we're going to be cool kids. We're going to be the cool kids on campus and plug in some useful values. What's a good value between 0 and pi? Pi over 2. Could be good, especially since we're dealing with sine. And x equals 3 pi over 2. That should also be a good one. But there's nothing stopping you from doing pi over 4 and 7 pi over 4, or pi over 6 and 11 pi over 6. Nothing stopping you from that. But sine of pi over 2 is positive 1. So it's going to be, oh, I meant to write that in black. Positive, so it's going to be concave up between 0 and pi. And then if you plug in 3 pi over 2, you get sine of 3 pi over 2 is negative 1. So it's going to be negative here. So it's going to be concave down. So concave up from 0 to pi, concave down from pi to 2 pi. And then there's an inflection point at x equals pi. There's an inflection point at x equals pi because concavity changed and the function exists there and is continuous there for furthermore. So we need to find the location. So g of pi would be approximately, well, actually, it's exactly pi, which is approximately 3.14. So we have pi comma pi, which is approximately pi comma 3.14. Why did I do that? I'll explain why in just a moment. The y values of the function are going to be a little bit stranger. If I like, so I could have written pi comma pi, and that would be fine. But with regards to the y coordinates, 5 pi over 3 minus 2 sine of 5 pi over 3. 5 pi over 3 is the big number. So sine would be square root 3 over 2. So you get 5 pi over 3 minus square root 3 over 2. Sorry, plus square root 3. And that's not a nice number. So I'm going to use approximations for the y coordinates. The x coordinates are nice and neat. So we got everything we need. Everybody good? So I'm only working on the interval from 0 to 2 pi. So I only really need the right half of the coordinate, plane. What I'm going to draw, and I would like if this was a problem on the exam, I would definitely give you this, a nice graph to work with. But it's going to look roughly like this. Make sure you have a little bit of space on the bottom. You don't need too much. I'm going to do 3 tick marks. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. And then because I know that all of my critical values, all the places where my curve is going to shift and change are all nice angles, I'm going to break my my curve up by increments of pi over 3. So here's 2 pi. Half of that would be pi. Break that up into thirds. So this is pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. I'll let you draw that graph because it's hard to do. Okay. Everyone have it drawn? I don't want to continue on unless everyone has the graph drawn. Underneath it, we're going to do our little cheat sheet by doing the sign charts for G double prime and G prime. I guess I don't really need to draw arrows, but G prime and G double prime. G prime had 0 pi over 3 and 5 pi over 3. And then here's 2 pi. And then G double prime had just 0 pi and 2 pi. We'll draw vertical lines wherever we see a tick mark that we made. Legitimately, the way that I learned how to do this, I just had to keep following my hand. I just kept looking at my hand to figure out what the shape would be. Don't recommend that. This makes a lot more sense, at least to me. But there are plenty of other alternate explanations, by the way. If you want to, feel free to look up online. Khan Academy is a great resource. Other people on YouTube have done similar things and explained it in different ways. So please feel free to use alternate resources. But rewriting this, it was decreasing, increasing, decreasing, and it was concave up, and concave down here. So I want you to fill in the whole chart. Realizing if you're decreasing and curving upwards, you should look like this. That's what you should get. The first two should form a lower half of a circle. The second two should form the upper half of a circle, if you're drawing it the correct way. Any questions so far? A lot going on. These problems take a while. Make sure you bring a Chewy bar with you or something, or a Cliff bar to give you some energy after halfway through. It's a lot to work with. Yes, Avery.
Gonna say because they take a little bit of time to do, is there like, what would be like the most like time efficient process of how to do it? Like, would you just like stop about it?
Just go top to bottom. Usually with these types of problems, I like to break it up into pieces. I'm not going to say just sketch the problem and give you a blank graph. I probably put like find where it's increasing, decreasing, find where it's concave up, concave down, and inflection points, then graph. And I'll make sure that, as I said, if there's a graphing problem, I will make sure to have those two little bars at the bottom so that you can make your little cheat sheet. Now that we've got that all done, we're going to plot any important points that we found. So we had 0, 0 as an X and Y intercept. We had a relative maximum at 5 pi over 3, 6.97. So 5 pi over 3, 1, 2, 3, 4, 5, 6. And it's basically 7. So right about there. So right about there. It doesn't need to be perfect because this is an approximation. We had a relative minimum at pi over 3, negative 6.8. So right about there. And we had an inflection point at pi, pi, or pi, 3.14, which will be roughly there. We could find the endpoint at 2 pi if we really wanted to finish off the graph and find the exact endpoint, but it didn't specify to do that, so we don't really need to. But we know it's curving downwards. It's curving upwards, but going down. So it's going to look like this. And then it's going to start curving upwards and increasing. But then at pi, it's still increasing. Like after pi, it's still increasing, but it's curving downwards. It changes concavity. And then it starts to curve downwards to 2. And since we didn't know what 2 pi was, you'll find out it actually ends up being 2 pi, which is 6.28-ish. But either way, you can just call it good like that. And there we have it. Tough problem, I know, but we're stronger mathematicians for it. We just exercised our trig section. It's like your back muscles that no one wants to work on, like those little interior, like not the deltoids and the trapezius and the latissimus dorsi, those little interior muscles that cause you to have a bunch of back pain. Those ones you need to work those every once in a while. Otherwise, you'll be like me and have constant back pain. So, anyways, any questions on that? All right. I'm gonna skip this one. I'll make a video on it to show you how to do this problem because it is still a good practice problem, but it involves a slant asymptote, which I'll tell you definitively, there's not going to be any slant asymptote problems on the exam. I'd say this is more of a homework problem type situation or like an experimental problem for class, but I want to get started with optimization as soon as possible. So I'll post this. It's good practice for finding increasing, decreasing, and so on and so forth, but finding the asymptotes, that's just kind of a tedious extra thing. You already did that in 126, so why spend the time on it? And we get to optimization. So I hope you understand, like I think I mentioned it, this is the reason why it's taking me so long to write exercises for 3.4, because it's just so hard to find a function that has a nice factorable first derivative, a nice factorable second derivative, and the critical values and the inflection point possibilities are nice numbers. It's just so hard to do. Like it's awful. It's the worst. So optimization, another one of people's favorite sections of calculus of 181, because it's word problems. Everyone's favorite, I know. So this is an actual very, very useful thing. And this, I'll give you one thing of truth is that the sad fact is the problems that we're going to be doing here are very, very contrived, right? It's like finding the maximum minimum of this weird situation that will never actually happen. However, this is the start of doing it in multiple variables. So there, like this is optimization. Later on, you start talking about in Math 283, you'll talk about Lagrange multipliers. Lagrange was a famous mathematician, and he figured out how to optimize in 3 dimensions and more. Actually, it's actually generalized to n dimensions. So you can, like, this is the start of it, but it's used as a stepping stone to actually do real problems with optimization, which is going to involve multiple variables because life doesn't usually have just one variable of interest. There's usually lots of them. And so Lagrange multipliers are like the big boy version of this. But we still have to figure it out at first. So step 0, once again, just like with related rates, you got to read the problem. You got to take time to do it. If you have an optimization problem on an exam, read it carefully. There's a lot of information that needs to be parsed through. And so it's important to take time to do it. One thing I want to mention is that it is very, very easy. So on this exam, we're only going to have optimization problems, right? There's no related rates because that was on chapter 2. That's the reason why, yes, it is technically an application of differentiation, but I did not want to put optimization and related rates on the same exam. However, the final exam is cumulative. So the final exam could have related rates or optimization problems. But the good news is there's a very, very quick way to find the difference. Related rates will have, quote unquote, rate of change. I'm going to put the of change in parentheses. So if you see find the rate or find the rate of change of blank, that's a related rates problem. That's a related rates problem. You don't need to think about anything else besides doing related rates techniques. Whereas optimization will have maximum / minimum / optimize. So if it says find the maximum volume or find the maximum height or the minimum radius, that's an optimization problem right then and there. So that's the way we distinguish them. Related rates, you should see the word rate in it. If you don't see the word rate, it's got to be an optimization problem. And vice versa. If you see a maximum minimum, it's not going to be a related rates. So that's not going to be necessary for this exam, but it is going to be necessary on the final exam. I don't remember the final exam is departmental. So I don't get to see it until the very, very end of the semester because it's written by the department. And it could be that they have a related rates problem and not an optimization. It could be that they have an optimization and not a related rates, or they could have both, or they could have neither. Let's hope for neither, right? Fingers crossed for neither. But in the event, that's what you do. Step 1, after you've read the problem and identified that it is an optimization problem, you're going to draw a picture if it's possible. Once again, a picture is worth 1,000 words, so it can help you get started. If you draw a picture with the problem, I'll give you a point of credit, at least 1 point of credit on the problem. Even if you don't know where to go, draw a picture, you're getting started. Step 2, write down any relevant information. This will usually be 2 things. You'll get 2 equations. One of them is what I call the optimizing equation. And so this will involves the quantity that you want to optimize. Whether it be volume, radius, circumference, whatever it may be, it should have it. Your optimizing equation should have a way to optimize the variable in question. If it doesn't, it's not the optimizing equation. Now, as an aside with this, so I'm going to underline this. This is not standard notation. This is not a standard definition. So I'm not going to treat it as such. It's my own terminology. It's an optimizing equation. It involves the quantity you want to optimize. Now, sometimes this will have 2+ variables. If so, you'll need to substitute using the equation below. Let you write that down. The optimizing equation is the thing that you're trying to maximize or minimize. But more often than not, if I'm asking you to optimize a cylinder, like the volume of a cylinder, V is equal to pi r squared h. That's 2 variables. And how do we take the derivative of a 2-variable function? We cannot in this class. That's a 283 concept. That's math 283 when we start working on partial derivatives. So there's no way for us to do that. So if you have multiple variables, you're going to use the substitution technique with the next equation, which I like to call the constraint equation. And a constraint, by definition, is a bound. It's a stopping point. It's something that's preventing you from doing something. So a constraint equation involves a bound of some sort. This involves a bound, quote unquote, which will allow you to write one variable in terms of the others. For substitution purposes. By the way, this is all very, very generalized right now, so it doesn't really make, I'm assuming it might not make too much sense at the moment. But once you see it in action, you'll say, oh, okay, I see what the optimizing and constraint equations are. So let's get through this, and then I'll come back to it and explain. Step 2.5 is a sub-step. So not every equation, not every single problem that involves optimization will have both of these equations. Sometimes it doesn't need a constraint equation, right? If I'm trying to maximize the volume of a square, or maximize the area of a square, the length and the width are the same thing. So trying to find the derivative, not too terrible. It's all going to be a single variable. So in certain circumstances, you won't have a constraint equation, or it will automatically fall out by necessity. You'll see. But if you do have that situation, if you do have a constraint equation, if you have a constraint equation, use it to make the substitution into the optimizing equation to create a function of a single variable, because this is single variable calculus. Math 181 is just called calculus 1, but it probably would be more aptly described as single variable calculus part 1. 182 is single variable calculus part 2, and then calc 3 is multivariable calculus. Now that you've got a function of a single variable, we know how to optimize that. We can find the derivative, set it equal to 0 to find critical values, use the first derivative test to find where it's increasing and decreasing, therefore relative maximums, or decreasing and increasing, and therefore relative minimums. And be careful about the domain. Sometimes you'll find extra critical values that aren't feasible within the constraints. And then make sure you test endpoints if you're working on a closed interval. And be sure to verify that it's a max or a min. I will mark down if you don't verify, right? I don't want any of my students going on to build bridges and not verify that it's structurally sound. Don't want anything breaking. That's actually poor taste, given what happened in Baltimore recently. Was it Baltimore, or was it just in Maryland? Someplace there's a bridge that collapsed. It's awful. So we're gonna just forget that I made that joke. But I want to make sure that you're not gonna be an engineer who forgets to do it, or maybe the Apollo 15 or whatever it was, the one that they didn't check the O-rings. I don't want that to be you guys. Okay. So we got to verify our maxes and our mins. And then step 4 is to answer the question completely. If it asks you to find the maximum volume and you found the side length, you need to plug it in and find the volume. If it just asks for the side length, leave it as is. Make sure you're actually answering the question. And here, as per usual in my class, I want to round to 2 decimal places. So you will get marked down if you do not verify. Only a point or so, but still. So I need to edit this problem. I need to edit it. Did I make a comment to myself to edit this problem? It's 3.5.1. Yeah. I didn't change it yet. I didn't change it because this problem makes no freaking sense in that context. So let's read it though. A ranch has 200 feet of fencing. That's it, 200 feet. It's a ranch for squirrels, apparently. Has 200 feet of fencing, which is being used to enclose 2 adjacent rectangular plots that share a fence. What dimensions should be used to ensure that the enclosed area is maximized? So imagine we're not in the 3.5 notes and this was a question on the exam. You see this word maximize, and that tells you everything you need to know. This is an optimization problem. So we've read it. We've identified that this is an optimization problem. Let's draw a picture. And so we got this rectangular plot. I don't know why I didn't just draw a rectangle. So like this. And then we don't necessarily know if it's going to be optimized by having them 2 adjacent rectangular plots that will share a fence. So I think what we want to say is 2 equal rectangular plots, but like this. And so you've got a little brown cow over here. And maybe a chicken on the other side. No, yellow. They have orange feet, don't they? And Bill, is this absolutely necessary? Didn't you say that we were running out of time? Yes. And then orange beak. Looks like a duck, but whatever. Maybe it's a pecking duck, you know. Maybe they're farming for that sweet, sweet duck meat. Okay. We've drawn our picture. We've had a great all time. We're having fun. So we've got a rectangular plot. We don't know the dimensions. That's what's being asked. We're trying to find the dimensions that will maximize the area. So this is the fencing that's all around it. The black is the fencing. So I'll call this X. And then remember, this is also part of the fencing. The middle one is also part of the fencing. So that's X as well. Now there's 2 options here. We could either call this Y and this Y as well, or we could call the whole thing Y. Since it is a full line across the same thing, it's not like jagged. We're assuming that the rectangular plots of equal size. So we could either make like one rectangular piece have a Y, or both of them called Y. Which would you guys prefer? One Y? That's fine. It doesn't, like, at the end of the day, you will get the exact same answer, except your Y will be half as big if you do Y and Y. If you do Y, Y like this, then your answers for Y will be half as big, but that's okay because that's the correct measurement based on your problem. It does not matter which side which one you choose. So we're trying to maximize area, right? So that's going to be the optimizing equation. Optimizing equation is going to be area of the rectangle. And the area of a rectangle is length times width. So in this case, that would be x times y. Be careful. If you decided to do y like that, what would your area be? It wouldn't be x times y, it would be x times 2y. So just in case you want to do it like tomorrow or this weekend or something like that, and you want to try it a different way, make sure that the dimension on the bottom would be 2y if you were making each individual square have a y. But the area for mine, since I've made the whole width y, is just length times width, so it's x times y. Then, the problem here is this is a two-variable equation. So I can't take the derivative of it. I don't know how to take the derivative of a multivariable equation. I mean, I do, but that's because I've taken 283. You guys have not. You're still in 181. So there's a problem. But what piece of information have we not used? The 200 feet of fencing. That hasn't come into play. That's a bound. The farmer can't use more, the squirrel farmer can't use more than 200 feet of fencing. So we have a constraint equation. If we add up all the side lengths, it should only be at most 200. And since we're trying to maximize it, we should definitely use all 200 feet of fencing. So I have two y pieces of fencing and 3x pieces of fencing. So I have 3x plus 2y is equal to 200. That right there is a constraint equation. It gives me a bound. Any questions so far? So the constraint equation will now allow me to write one of the variables in terms of the other. It does not matter which one you choose. Either way, you will get the right answer. I would recommend solving for y because then I get a nice integer number when I divide by 2. But you can solve for x. It's fine either way. But I'm going to do it this way. So I'm going to get 2y is equal to 200 minus 3x. That tells me y is equal to 100 minus 3 halves x. Yeah, we have to deal with one fraction, but you're going to have to deal with fractions either way. And this time we only have to deal with one. But it's fine to do it the other way too. Once again, great icebreaker if you're becoming part of a team. I found out so my son's playing is playing soccer right now. He's on the team, and they don't know each other's names. So because like we didn't have a coach, so we didn't know what to do. None of us have ever been on a soccer team before, so we're all just winging it. And one of the parents decided to step up. Thank you, Coach Allie. But I realized after the fact that you should really open with an icebreaker so that they can get to know each other. So I'm saying like Phoenix, kick it to Amani. Who's Amani? I don't know. But anyways, where was I going with that? Where was I going with that icebreaker? Oh, be a great icebreaker to do when you're getting together. Have one of you guys do it by solving for y, and one of you guys solve it for x, and see if you guys get the same answer. If you didn't, you can call one of the people the idiot, right? That's excellent. Great way to break the ice. Anyways, I'm getting sidetracked. Your guys' fault, not mine. What I'm going to do is I'm going to take this expression and substitute it in. For y. So this means that a will now equal x times 100 minus 3 halves x. And so this is a small minor change that I'm going to make that you don't have to write, but I want you to write it to understand the significance here. Now I have a function purely in terms of x. I have a of x. Before it was a of x comma y. Now it is a of x. And it's going to equal 100x minus 3/2 x squared. And that's a function that's of a single variable, and we know how to find the places where that's increasing and decreasing, and therefore the places where it's going to have a maximum and a minimum. Now, one thing that is of note, it's not going to be relevant for this problem, but it might be relevant later on. So I'm going to put it kind of as a side note over here. Note the domain of x is parentheses 0 to 200 divided by 3. Take a second to figure out why. No, not the variable y, not the domain of variable y, but the why the domain of x is 0 comma to 200 thirds. Does anybody see why? This thing, it could look like this. It could look like this. I doubt that those are going to be the answers. That's probably not going to work. You can't even fit a cow on that situation, but it could vary in a lot of different ways. So in particular, you could have, technically speaking, you could make the pen have 0 height. So that would mean x being 0, but then it wouldn't actually have any area. So we can't include 0 because then you wouldn't really do it. I mean, I guess you could, but it would be irrelevant. And on the flip side, you could make it 3 lines because there's 3 x's, right? So you could use all of the fencing on those 3 vertical lines, meaning that since you only have 200 feet of fencing, it could be 200 divided by 3. That's not going to be useful in this problem, but it is still relevant for other things as well. Anyways, any questions on why that's the domain now? It's okay if there are questions. I can explain that differently. Yeah.
Wait, so we said it can really be 0, but it's still.
So like the argument, like, so I'm going to say it's parentheses. I would accept you putting it as brackets because I guess technically speaking, you could well, no, you can't. You can't make a rectangle with it if it's just 2 lines. There's no width. And so it's just a line. So that's why I would say the parentheses. I'm not going to mark you down if you say a bracket instead. It's not a big deal. That's mainly just to make sure that we don't test critical values outside of that interval. This one won't have any, but sometimes they do. So once again, like we've done a lot of stuff here. Let's recap one real quick. We had an optimized equation, but it had 2 variables. So we used the constraint equation to represent one of their variables, y, in terms of x, and then plugged it in to finally get a function purely of x. The reason we did that is that now we can find the optimization. How do we optimize it? We got to take the derivative to find the critical values to find where it has relative maximums and minimums. So a prime of x would be 100 minus 3x. And we're going to set that equal to 0 / d and e. You get 100 minus 3x equals 0, which gives us x equals 100 thirds, or 33.33 feet. 33.3 repeating. Now, John Doe student says, oh, perfect, that's the answer. Why is John Doe student wrong? You don't know if that's a maximum or a minimum. You got to verify. So verify a max. So we're working on the interval from 0 to 200 over 3. And then 100 thirds is right in the center there. But you can plot it wherever you want, actually, if you really feel passionate. But either way, we're going to pick 2 numbers to test values. X equals, I'd say 1, and x equals, let's say, 100 thirds is 33.3, so 34. 35, let's just be safe. I didn't use a calculator to verify. 35. Plugging in 1 into that, you'll get positive number. And it'll be increasing the function. So the area function will be increasing as you go from 0 to 100 thirds. Then at 35, we plug in a test value. 100 minus 3 times 35. 3 times 35 is 115, right? No, 105. So it's going to be negative, but you can use your calculator, of course. So it's decreasing here, which means that it's a maximum, max verified. So we know that's the right answer. So while people are writing down a reminder, I took the derivative because I'm going to find the critical values, because the critical values are where the relative extrema will occur. And I'm trying to find a relative maximum area, or trying to find a maximum area. So I'll test that value. I'll verify that it's a maximum. And then John Doe student says, I got the answer then. X is equal to 100 over 3 feet. And he boxes this in. Why is John Doe student wrong? We still need the y. It says, what are the dimensions? It doesn't say what is the x dimension. It says, what are the dimensions? If the question asked, what was the maximum area? We multiply the x and the y together. But it's just asking for the dimensions. But this is not a hard thing to do, because we already have an equation right here that represents y in terms of x. So we can solve for y using our constraint equation. So y will equal 100 minus 3 halves times 100 thirds, which will equal 50 feet. Now, I guarantee you, if you decide to do it where you make each individual box have a y, your y value will be 25, which makes sense. It should be 2 of them. That makes the full thing. So either way, I like, if this was the problem on the exam, I'd be giving you credit full regardless. So any questions on that? Yes, Bailey.
So the answer is just x equals blank and y equals blank. There's no other like notation for, that's it.
That's it.
Oh.
And in fact, because it's mentioned in the problem that we're dealing with feet, I might be okay if you just write x equals 100 over 3 and y equals 50. I mean, ideally write the units of measurement, but it's you can bust out my own terminology against me, a mathematician's terminology against them, and say it's clear from the context that we're talking about feet. Yes. Dave.
Just making sure that we're not using any of the fencing as part of the center where there's a fence.
No, we are. That's why it's 3x instead of 2x. Yes. Excellent question. And there's so many different types of these problems. I know. So this is a very contrived problem, right? 200 feet of fencing doesn't make any sense. And also, why are they sharing a fence? That seems like a bad idea. Yes.
Split the y up, it would be 4y instead of 2y.
Exactly right. Yes. So Diego makes a great point. If you had decided to do this, y, and y, it would be x times 2y, and this would be 3x plus 4y equals 200. It still equals 200. You only have 200 feet of fencing. But either way, I encourage you, if you're bored, trying to fall asleep, try that. I guarantee you will get the same answer, just in a different format. All right. Kind of a fun problem though, right? Then this one, if you guys remember, I love these problems because it reminds me of Lindsay Lohan and good old Mean Girls. Find 2 numbers such that the smaller number is twice the second number, and the first number times 2 times the second is a maximum or whatever. Remember that question in the math decathlon situation? Please tell me everyone's watched Mean Girls. Has anybody not watched Mean Girls? You must watch. You must watch. It's a cultural icon. It's amazing. It's like Lindsay Lohan's best movie. Either way, that just reminds me of that thing. That guy solved it way too quickly. I don't know how that was possible, but find two positive integers such that the sum of the first number and twice the second number is 108 and their product is a maximum. So can't really draw a picture here, but the fact that it says maximum tells me I'm dealing with an optimization problem. So I can't draw a picture because there's not really, integers are a mathematical quantity. They don't have a picture to them, but I need to define them. If I just write, so let x equal the first integer and y equal the second integer. So what am I trying to optimize? I'm trying to optimize their product. Now, because I don't have there's no mathematical statement for an equation. It's not like area where you have area equals length times width, or volume equals 4/3 pi r cubed, or whatever it is. So I have to make up a name for it. I'm going to call it product, so I'm going to call it P. So optimize the product, which is going to be the product of the first and the second integer, so that their product is the maximum. If I said the product of the first and 2 times the second, it would be x times 2y. Or if it was the product of the square of the first and the second, then it would be x squared y. So keep in mind the terminology. So that's the product, but that's a 2-variable equation. That's an x and a y. That's p of x comma y. So there must be a constraint. Constraint being what? The sum of the first number and twice the second. So sum meaning addition, twice the second meaning 2y. So it should be that x plus 2y has to equal 108. Any questions so far? So it doesn't matter which one we choose. Do you guys want to use X or Y to solve for it? There's a clear choice who's better, but both work. Solve for X. Yeah, nice. So I would recommend that. So X is equal to 108 minus 2Y. And this allows me to take this. Sure, we'll do a parallelogram and plug it in for X. So now we get P of X. Could you imagine if I just wrote all my notes with dotted lines? It'd be awful. P of X, sorry, P of Y, excuse me, is now 108 minus 2y times y. And technically speaking, y could be at minimum 0 and at maximum 54. Think about why. So note, domain of y is parentheses 0 to 54. I guess technically speaking, you could include the endpoints here as well, because but it says positive integers, so 0 can't be included. But if you plug in 0, then you can make this first number just 108. And if you just make the first number 0, then y would have to be 54 in order for it to be twice the second number equal to 108. But either way, that's just for filler stuff. So P of y, simplifying it, that's 108y minus 2y squared. And that is a single variable equation, which we can maximize. Take the derivative, set it equal to 0 to find the critical values. The critical values can give you relative extrema. So P prime of y is 108 minus 4y. Setting P prime equal to 0/DNE. To find the critical values, you get 108 minus 4y is equal to 0. That gives me y is equal to negative 108 divided by negative 4, which is 27. But I don't necessarily know that that is a maximum or a minimum. I have no way of knowing until I verify it. Now, one thing you could do is you could use the second derivative test, by the way. because we're not looking for where it's increasing or decreasing, we're just looking for extrema. So you could just take the second derivative, which would just be -4, and since it's always gonna be negative, that means it's gonna be a relative maximum. So you could use the second derivative test, but why would you? It's just an unnecessary test until you get to 283 when you have to use it. So we'll verify. We're working on 0 to 54. And here's 27. And yes, I know that this is also the midpoint. It was the midpoint before, and it was the midpoint again. That's not always guaranteed. So don't just assume that you can find it. And furthermore, when it comes to my exams, I need you to show me the calculus. So if you just guess that it's 27, I can't give you any credit, really. Cool for noticing patterns, but not sufficient. So I'll plug in x equals 1, or sorry, y equals 1 and y equals 28. This is p prime. So plugging in 1 into this equation, it'll be 108 minus 4. That'd be positive. So it's increasing. Plugging in 28, you can use your calculator, but I guarantee you when you plug it in, you will get a negative number. And so it's verified. Max has been verified. So your y value is 27, but it's saying you want to find both integers. But that's not too terrible to figure out because we have a formula relating x and y. So we just plug it into the formula. 108 minus 2 times 27, which equals 54. Any questions on that? If you don't define what x and y are here, then I have no idea which one was the first variable and which one was the second integer. So I might have to mark you down 1 point. So please define your variables if you're using them. If it's clear from the context, like this situation where it's a drawing of a graph, you've told me that x is that length and y is that bottom length, it's fine. But if you're going to create an equation from scratch, please tell me what the integers are. Remember, you're trying to show this to a colleague, and they should be able to look at your work and understand how everything's working. Okay, that'll be it for today. If you have any questions, feel free to email me. Otherwise, I'll see you guys next time. We'll pick up with the rest of this, and then we'll move on to 3.6 and 3.7. All right? See you then. Have a great weekend.